If you recall, yesterday we looked at a new multiplication problem. Work is equal to force times distance. We're going to take this multiplication and turn it into a calculus problem by making one of these factors a continuously variable function of the other. So we had to write a function for, we created a scenario where the force or the weight of this bucket was changing continuously over the 12 feet as it moved up. So I couldn't just multiply the 200 pounds times the 12 feet. We also talked about the fact when we could use the average. The reason that we could use the average is that the scenario we set up yesterday was the function changed linearly from 200 to 180. So all the change was balanced around the 190 pounds at 6 feet. So we could get away with using an average if we, specifically the average of the 180 and the 200, we can get away with that average of 190, specifically because we talked about a linear function. So recall, hard to make sentence today. So recall, if the force changes in a linear fashion, if the force is a linear function of the distance, then we can just average the 180 and the 200. If the force is a linear function of distance, like it was yesterday, that's what allows us to use the average of the force of the buckets at the end points. So we could just say 1/2 of 180 and 200 is 190 pounds, and multiply that by 12 feet. And that gave us the value that we had yesterday, which I can't recall. I could totally do the calculation if I wasn't. Oops. 2280. This is the value that we had yesterday, and that was 190 times 12. This works. We were able to do the average. 2280. We were able to do the average because the force was a linear function of the distance. Linear is our default. And the average of the endpoints is just going to give us a linear function. The average of the endpoints will always just give us a linear function. Think back to when we were finding area under the curve. The trapezoidal rule was the average of the left and right, because a trapezoid is just an average of the two rectangles that contain it. So a geometric way of thinking about this is a trapezoid is an average of the two rectangles. A trapezoid is going to be the average of two rectangles that have the same height. So if we draw one rectangle with a base of B1 and a height of H, and we draw another rectangle with the same height of H and a base of B2, then the trapezoid is just the average of these two rectangles. And we can draw a trapezoid by connecting the two corners with a line. Here's our linear function. The area of the trapezoid is just the average of the two rectangles. So we're taking base 1 times the height plus base 2 times the height and dividing them by 2. And that gives us our usual formula for a trapezoid: 1/2 base 1 plus base 2 times the height, where we factor out the common factor of 1/2 and H. When you find an average at the endpoints, you're making things linear. You're thinking about a linear change from one point to the next. So that's why in this particular problem, we can get away with doing the 190, because it's just the average of the endpoints, because we made a linear function connecting the 200 to the 180. So what if we use just some different kind of function? Then our average wouldn't be 190. So let's suppose that we had an exponential function from 200 down to 180. So let's suppose that we changed our type of function and we decreased exponentially from the 200 pounds to the 180 pounds in 12 feet. So we'd have to set up a different function rather than saying 200 minus 20 over 12 times x. I'd have to install a multiplier. I'd have to say our force would start off at 200. And then we multiply down to 180. So we start off at 200 when x is 0. I know x hasn't shown up yet. In a second. We start off at 200 when x is 0. And we want to multiply by the new value divided by the old value. So we're going to multiply by 180 over 200. But we don't want to do this in 1 unit. We want one multiplication of 180 over 200 to take 12 units. So I'm gonna have to change my exponent to adjust for this 12 feet. So we're gonna raise this to an exponent of x over 12. So we want to start with 200 and we want to multiply by 180 over 200 one time when x equals 12. That's what's going on when we write this function. We start at 200. Force starts at 200 when x is 0. We want to decrease down to 180. That means we want to multiply by 180 over 200. So we're going to multiply by 180 over 200. The reason that we want to multiply by 180 over 200 is because we want to end up at the 180 starting from 200. So if we take 200, multiply by 180 over 200, 200's cancel, we are left with 180. This is just the multiplication version of what we did yesterday. Yesterday, we wanted to end up at 180 by addition. So we wanted to subtract 200 minus 180 from the 200. One time when x increased by 12. So we wanted to multiply by 180 over 200 one time when x hits 12. So multiply by 180 over 200. Once when x is equal to 12. Notice that when x is equal to 12, that exponent is 1, which means we multiply by 180 over 200 one time. When x is 12, that exponent x over 12 is 1. So we multiply by the 180 over 200 one time. Technically, we built the linear function the same way, just with addition instead of multiplication. So we had to use multiplication instead of exponents. But typically, that's not how we're taught exponential and linear functions, but that's okay. So now, if we want to figure out the work done, this is the force that we're going to use, and we're going to use it for the same distance, delta x. So our work is going to be our force 200 times 180 over 200 to the x over 12 times delta x. So our total work I can factor out this 200 because it's a constant factor. We're going to integrate this function 180 over 200 . So that's going to be 0.9. Our delta x, our discrete delta x becomes a continuous dx. And we integrate over all the values of x that are in play, and that is from 0 to 12. That's how the distance shows up in our work integral. We integrate the force over the distance. That means the 12 feet of distance is from 0 to 12. Then we grab our calculating machine and we do 200 and F an integral, 200 math 9 for an F an integral, and we want to do 0.9 to the x over 12 with respect to x from 0 to 12. 2277.89. So 5 significant figures would be 2277.9. Pound foot. In this case, we did not get the same as we got with the, we did not get the same when, as when we had the function. We did not get the same as when we had the linear function. The linear function was balanced in the first half and the second half. Here, it's not, our function is not going to be balanced. We didn't just connect the 2 points with a line. So we didn't have the same value above and below. We didn't connect things with a line. If we integrate from 0 to 6, if we look at the first half, if we integrate from 0 to 6 of the 0.9 to the x over 12 to x, and the second half, 200 times 0.9 to the x over 12, the x. So in the first half, we'll integrate from 0 to 6. And we get 1168, and that is not half of our 2277. The second half will integrate from 6 to 12, and we get less, 1108.95. Yeah, dang it. I even said it out loud. 1109.0 pound foots. This wasn't the case when we had the linear function. In the linear function, everything was nice and easy, split around the middle. So I think I still have this here. So here was our f an integral from the linear function. That was the 181. Let's do the 201. So that's how I'm going to be talking about this. So there's our 2280. Now, if we integrate from 0 to 6, or 6 to 12, 1110, and from 0 to 6, did I just not make the point that I wanted to make? Well, I'm clearly thinking about something wrong. Dang it. That made so much sense this morning when I was thinking about talking about this. I'll worry about fixing it later. I think I'm distracted because the real thing I wanted to talk about was how to build the exponential function. And I wanted to see how similar, how we build the exponential function in the same way that we build the oh yeah, it's not going to be balanced. I'm done. What can I say? What I really wanted to talk about was building the exponential function in the same way that we built the linear function. So if you think about when we recall the linear function, when we're building a linear function, our change is by addition. Our change is going to be repeated addition expressed with multiplication. So we're going to add, I'm going to build this linear function the same way we built the exponential function. So I'm going to start with 200. I'm going to change by addition. So I want to know where I want to end up. I want to end up at 180. So the change is going to be, I want to add 180 minus 200. That's going to be adding a negative 20. I want to add negative 20 one time when x equals 12. So if I want to multiply this by x over 12. So that's what's going on with the linear function. We want to start with 200. When x is equal to 0, I want the force to end up at 180. So I want to add 180 minus 200. Normally, we would just call that negative 20. I want to add negative 20. And moreover, we would just say, I want to subtract 20 one time. But I wanted to see that this 20 came from where we ended up minus where we started, because we're using addition. So we want to look at the changes thinking about addition. So the force is 200 when x is 0, and we want to add negative 20 one time. So I'm going to phrase it the same way. I want to add 180 minus 200, or negative 20, one time. And I want that to happen when x equals 12. I want to add negative 20 once when x is equal to 12. So when x is equal to 12, this multiplier, this factor out here, tells us how many times to do this addition. X over 12 is the factor that counts the number of times you do the addition. This is how linear functions work. This factor with the x that factor counts the number of times we do the addition. It's included as a factor. It's included with multiplication because multiplication is repeated addition. It's a factor since multiplication is repeated addition. Now, I'm not saying that we learn how to build linear functions wrong. It's not wrong, say b plus m times x. It's not wrong to say mx plus b. But it hides a lot of the thinking that goes behind the linear function, makes it mechanical, and we lose perspective on how things work. If we knew how things work, if we understood the operations better, and we understood what we were doing with the linear function, then when it comes to building an exponential function, it wouldn't be a problem. I would just be able to say, remember linear functions? Now do the same thing, but with multiplication. So instead of looking at linear functions as y equals mx plus b, for this one, I see this and I see Drake disapproving. A better version, start off at b and add the rise x over run times. Instead of combining the rise and the run into the coefficient and say add the rise over the run x times, we could also think about adding the rise x over run times. It's efficient to put the rise and the run into one coefficient. We can do that here because it's multiplication and division. X over run is division, multiplied by the rise is multiplication. That's all the same operation. So I can commute those. And instead of x divided by the run, then multiply by the rise, I can take rise, divide by the run, then multiply by x. That certainly has some utility. It changes when we switch our operation from addition to multiplication. Because here I want to do repeated addition with multiplication, but repeated multiplication is an exponent. And so now I can't just move things around and do rise divided by run. I would have to do the run root of the rise. Rise to the 1 over n. Addition. I spelled D wrong. I just spelled DB. If I did that while I was grading, that would be kind of awesome for the students. What'd you get in math? I got a D, but he wrote B because of a typo. So there's the operation of addition. How many times do you want to add the rise? I want to do that operation x over the run times. I want to add the rise x over the run times. X over the run is counting the number of times we add the rise. Here we have multiplication. And so I want to take b and multiply by the rise a bunch of times. Repeated multiplication is expressed with exponents. The reason that I point this out is that most people go through exponential functions doing some really weird shit. But you can build exponential functions without doing any calculations. You can avoid the calculations. Your traditional exponential function technique would be like, oh, y is equal to a times b to the x. And if we have 2 points, say 0, 200, and 12, 180, the traditional exponential function technique, the algorithm that you're programmed to follow to find a and b, is to plug the 2 points into the equation. So write 200 is equal to a times b to the 0, and then 180 is equal to a times b to the 12, and then just, I'm putting this in quotes, divide the two equations. The 180 over 200, that's your multiplier. That's your rise over run, but multiplication version. You go from 200 to 180 by multiplying by 0.9. That's what that 180 over 200 is. The a's cancel out, and you get b to the 12. And then so you would solve for b. B is the 12th root of 0.9. And a clearly has to be 200. That's what I gave you the 0.0200 for. But we come by the same result if we just think about what we want to have happen. Our exponential function starts at 200. And we want to get down to 180. So we're going to multiply by 180 over 200. That's the 0.9. That means 200 times the 180 over 200. The 200 will cancel. I want to do this one time, but I want that one time to happen when x is 12. So that's why we raise to the x over 12. The number of times we want to multiply by 180 over 200 is once when x is 12. So our exponent should be x over 12. Now, if we rearrange this, we have all the same numbers. 200, 180 times 200 divided by 200 is the 0.9. This is still to the x over 12. If we rearrange this exponent here, this is going to be 200 times the 12th roots. I'm going to write it out, 0.9 to the 1 over 12. And then all that gets raised to the x. And this thing in the middle here is the 12th root of 0.9. We get the same result. But we didn't need to do any of these calculations. We didn't need to, we could just go with this first expression. Once I write the 180 over 200 as 0.9, but this is much more descriptive. This says start at 200 and decrease by 10% every 12 units. If we calculate what the 12th root of 0.9 is, 0.991, I can rewrite this function as 200 times 0.991 to the x. Now this offers us another description. This offers us a unit change description. Because of the 99, I'm going to put 0.13, use some extra digits. Here we can describe it as starting at 200 and decrease by, let's see, what's this minus 1? Decrease by 0.0, then multiply by 100. We'll do percents. Decrease by 0.87% every unit. So it depends on how you want it to sound. Well, we'll be starting off at 200 and decreasing by only 0.87% every unit. Oh, that doesn't sound so bad. No. Gentlemen, if we start at 200, we'll be decreasing by 10% every 12 units. 10% every 12 units. That sounds much worse. That sounds much better. So it all depends on what outcome you want. And how bad your audience is at math. Any questions? Comment? I'm not sure what point I thought I was going to be able to make. I knew it was lighter in the second half, and so it would be less work. Oh. Clearly, the rain was distracting me on the way. All right, that's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing. It's going to bug me what I was thinking about. Sometimes we think dumb things.